Today, I would like to present our work, Networked Scheduling for Decentralized Load Frequency Control. I will cover the following 5 aspects: introduction and motivation, formulation of problem, main results, an illustrative example, and summary. With the vigorous development of power markets, the degree of interconnection among power grid regions is increasing. At present, power grids have developed into multi-area interconnected power systems. Generally, there are 2 communication schemes to transmit data between neighborhood areas, that is, the dedicated channel and the open infrastructure. Since the latter has outstanding advantages over the former, such as higher flexibility and lower cost, it has been widely used in the communication of multi-area interconnected power systems. An important indicator to measure power system operation quality is the fluctuation in frequency, and load frequency control is widely used to maintain frequency interchanges at scheduled values and stifle frequency fluctuation caused by load disturbances. Under the open communication infrastructure, the sensor in each area collects data information. Then data is transmitted to the decentralized controller and the shared but band-limited network. The corresponding control commands are issued to actuators in each area respectively. However, due to the introduction of a network, the design and operation of load frequency control face some new challenges, such as node collision, data loss, and network-induced delay. Due to different locations of separation power grids and the wide distribution of system components, multi-channel transmission is inevitable in multi-area interconnected power systems. While most of existing results take the general assumption that sampled data is packaged into a single packet to transmit, it is not applied in the large-scale multi-area interconnected power systems. On the other hand, the shared network has limited bandwidth, while the simultaneous transmission and the multiple channels may cause node congestion. To solve this problem, scheduling protocols have been presented to decide which node to gain access to the communication network. Generally, multi-channel scheduling includes RR scheduling, TOD scheduling, and stochastic scheduling. In this work, we will study the decentralized load frequency control and the TOD or RR scheduling protocol. Let's discuss the next part. For the multi-area power system with n controlled areas and n decentralized controllers, the system model can be represented. Based on the phasor measurement unit, sampling instances of n sensors are synchronized in different areas of power systems. The series of sampling instances is a variable sampling sequence SQ. In an open networked communication environment, packet dropout and network-induced delay are inevitable. Denote the sequence after packet loss by Tk, that is, only at sampling instance Tk, the input of the controller can be updated. For the n controlled areas, an uncertain time-varying delay is assumed to occur. Buffers are set to store and choose the largest communication delay of power system channels. Then, zero-order hold updating instance is Tk, and the transmission delay is assumed to be bound. Denote Y height as the output signal transmitted to the scheduler. At instant Sk, only one node can be active. Under TOD protocol, the active output node delta K can be given by 2. Under RR protocol. LTK can be given by 3. And the scheduling protocols, the output signal transmitted to the scheduler is described as 4. Furthermore, we consider the scheduling errors EIT to describe the control input, and the impulsive power system model 5 can be built. Based on the closed-loop system model, our work is aimed to design the decentralized controller such that the studied system is exponentially stable with a prescribed H-infinity performance gamma and a TOD or RR scheduling protocol. Under such control objective, the main technical challenge is how to develop the sufficient conditions with little conservatism to ensure the exponential stability of the closed-loop system. To deal with this problem, we defined the Lyapunov functional candidate as Vt instead of the traditional Lyapunov functional. By using Lyapunov stability theory analysis, the sufficient conditions with little conservatism are proposed to ensure the prescribed system performances. Next, we will present our main results. In Theorem 1 and Theorem 2, the exponential stability of System 5 is ensured with the prescribed H-infinity performance. In Theorem 3 and Theorem 4, the decentralized output feedback controller and scheduling parameters are derived simultaneously to reach the prescribed performances concerning with the studied system. Next, we will verify the effectiveness of our result. We use a 3-area power system interconnected by the shared communication network to demonstrate the effectiveness of the main results. Parameters are listed in Table 1. In Case 1, we can obtain the decentralized controller gain K. Correspondingly, the state response and the switching behavior of active nodes are illustrated by Figure 2 and Figure 3. Clearly, the designed output feedback controllers can stabilize the system under TOD scheduling protocol in the absence of disturbance. Use the same parameters as Case 1, the controller gain can be derived in Case 2. State responses and the switching behavior of active nodes are depicted in Figure 4 and Figure 5. From Figure 2 to Figure 5, the system can be stable under both TOD and RR scheduling protocol. Compared with RR protocol, TOD protocol can achieve dynamic scheduling, which makes control process more efficient. In Case 3, we take TOD protocol as an example to verify the anti-disturbance performance of the studied system. And the disturbance omega t shown in Figure 6, we obtain controller gains, and state responses of the system are depicted in Figure 7. The designed decentralized controller and TOD protocol can ensure system stability with load disturbances. Finally, I would like to make a conclusion. This paper studies the H-infinity load frequency control for multi-area interconnected power systems with decentralized controllers and the shared but band-limited network. RR and TOD protocol are used to schedule the sampling information of different subgrids to greatly improve communication efficiency. Through linear matrix inequality technology and Lyapunov analysis method, sufficient conditions that guarantee the prescribed H-infinity performance of the studied system can be obtained. Decentralized controller gains and protocol parameters can be obtained simultaneously. These are main references in our work. Okay, ladies and gentlemen, it has been my pleasure to give you our reports. Thank you for your kind attention.